I am Dr. P.V. Tokar from Department of Electrical Engineering, Sanjeevani College of Engineering, Kopargaon. I welcome you all for session 3, and today's topic is effect of load power factor on regulation and efficiency. As you have seen this title, effect of load power factor on regulation and efficiency. First of all, we will discuss about regulation and then we will discuss about the efficiency. So starting with the point number 1, it is related with effect on regulation. Now already we have discussed about voltage regulation, so I will write here percentage voltage regulation is equal to IR cos phi R plus I into XL sin phi R divided by VR into 100. This is when the power factor is lagging. So I have written the formula for percentage voltage regulation for lagging power factor, that is IR cos phi R plus I into XL sin phi R divided by VR into 100. This is for lagging power factor. This is the expression for voltage regulation of a short transmission line. Short transmission line. Same formula I can write for leading power factor. For leading power factor, I can write the voltage regulation as IR into cos phi R minus I into XL sin phi R divided by VR into 100. This is for leading power factor. If you consider this particular 2 points, considering the regulation and efficiency, for regulation we have considered 2 points. Considering the lagging power factor, we have written the formula for voltage regulation as IR cos phi R plus I into XL sin phi R divided by VR into 100 for short transmission line, considering the lagging power factor. And for leading power factor, we have written the percentage voltage regulation as IR cos phi R minus I into XL sin phi R divided by VR into 100. Now for this case, we have to consider some points, that is when the load power factor is lagging. For this case, when the load power factor is lagging or unity or such that it is leading, then in this case IR cos phi R will be greater than I into XL sin phi R. So IR cos phi R will be greater than I into XL sin phi R. Then voltage regulation is positive. Voltage regulation is positive. Very important point to be noted. And second case is for a given receiving end voltage and current, the voltage regulation of the line, or you can say increases with the decrease in the power factor for lagging loads. Okay, now when the load power factor is leading, that is, in that case, when the load power factor is leading, this is for lagging, and for leading we can write when the load power factor is leading, then I into XL sin phi r will be greater than I into r cos phi r. So I into xl sin phi r will be greater than ir sin ir cos phi r in case of leading power factor. Then voltage regulation is negative. If IXL sin phi r is greater than IR cos phi r in case of leading power factor, then voltage regulation is negative. So please remember these points considering the regulation. So for this particular case, quickly revise the conclusion. The point number 1 is, when the load power factor is lagging or unity or leading, then IR cos phi r is greater than IXL sin phi r, then voltage regulation is positive. That is, receiving end voltage VR is less than sending end voltage. So VR will be less than VS. 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 And for given VR and I, the voltage regulation of the line increases with a decrease in the power factor for lagging loads. This was point number 2. Point number 3, when the load power factor is leading, then I into XL sin phi r will be greater than IR cos phi r. In this case, voltage regulation is negative for leading power factor. Now, if this for such a conditions, the receiving end voltage VR will be greater than VS. That is, for this case, when the voltage regulation is positive, then receiving end voltage will be less than sending end voltage, and when the voltage regulation is negative, then receiving end voltage will be greater than sending end voltage. And last point, point number 4, for this conclusion, for a given particular voltage, that is VR and I, the voltage regulation of the line decreases with decrease in the power factor for leading loads. Now considering point number 2, effect of transmission efficiency, effect on transmission efficiency. Now we know that in this particular case, if you consider the power delivered to the load, which is depend on the power factor for single phase and 3-phase line. So simply I will write power for single phase line. So power formula for single phase line is VI cos phi. This is the standard formula. In case of transmission line, V can be replaced by VR, load current is I, and power factor can be replaced by cos phi r. Therefore, from this formula we can write I is equal to P divided by VR cos phi r. So if the power factor is poor, then current will increase. If the current increases, diameter of the conductor increases. If the diameter of the conductor increases, cost of the conductor increases, material increases, and overall cost increases. So that is why the reason power factor should be maintained. Power factor should not be poor. Now this is what the formula of current, and what will happen if the power factor is poor. This is for single phase line. Now if you consider the three phase line, for three phase line we can write power is root 3 VL IL cos phi, VI cos phi, VL IL cos phi. Or in case of considering the three lines, we can write power is equal to 3 into VR IR cos phi R. This is for power for one phase. Therefore power for three phase, power for one phase and power for three phase. So 3 into VR IR cos phi R, like this we can write. And from here again we can write IR is equal to power divided by 3 into VR cos phi R. So it is it is clear that in each case, for given amount of the power to be transmitted, that is power P, and receiving end voltage VR, and the load current I, which is also IR. Load current I is inversely proportional. Load current I is inversely proportional to the power factor. I is inversely proportional to the power factor. So with a decrease in the load power factor, the load current, with a decrease in the load power factor, load current and hence line losses increases. Load current increases, line losses also increases. Load current with a decrease in the power factor, load current increases, line losses also increases. So this leads to the conclusion that the transmission efficiency of the line decreases with decrease in the load power factor and vice versa. So the conclusion is transmission line efficiency decreases with increase in the losses. So therefore if line losses increases, percentage efficiency of the transmission line decreases. So that's all from my side. Thank you.